All right, I think we should get started. I see people are still coming in, but it's 5 minutes past now, so I think in order to make sure we get through everything, I'll get started. Have a few announcements. I've announced it last week and also in an email that I sent out, but there is a feedback survey available on Blackboard, and I do appreciate it if you fill it out and give any comments on how things are going, if there's anything that could be improved. It's under the assessment and feedback section on Blackboard. It's labeled as the Week 3 survey. You should be able to go there and fill it out now. It closes on Monday, so next Monday at midnight. The other important announcement is about the diagnostic follow-up. And so you do have to complete the diagnostic follow-up by the end of next week. So that's by the 22nd of October. Is the end of the day on the 22nd of October, but you shouldn't leave it till the last minute. The assessment versions are now available, so you can do both the practice and assessment versions of the diagnostic feedback. And so, I suggest that you work on that earlier rather than later. All right, that's all the announcements. I was going to go over some material that was from last week, first of all, that I didn't get to in the last review session. And so this is about integration, finishing up a review of some of the concepts from week 2. And so we covered 3 methods of integration, which I mentioned last time as well. Integration by parts, and I put the formula for integration by parts there on the slide. Substitution, and partial fractions. And last time we did an example doing doing the substitution. And I'm going to do another example now. And so we want to calculate this indefinite integral. And for this one, you do have to use integration by parts. And so this will be the first poll for today. If you can connect to the Slido session via Blackboard. I hope a few people have done it. And do integration by parts on this integral. And you should get one of these 4 options. I'll open that up now. So I'll give you a minute or maybe a little bit longer to do this. It's also good waiting for people to come in. Yeah, it's the same review session.
There's another lecture after this one?
Or? It's the same. You can stay for this one if you want. Yeah, same. For the tutorial, it's different. You should go to the tutorial.
I have to go to this one.
Yes.
Some people have 2 hours.
I mean, the tutorials are at different times. Okay, in order to move on, I think we'll stop this now. I'll show you what the results were. So not too many people participating, but I hope as we move on, there are going to be some more of these. So please sign in. And that is the correct answer, number 4. So good job to everybody who did that. I hope more people will participate in the later ones, but I know a lot of people are just arriving. So let's go over how this goes on the visualizer as well. So we want to do this integral. X times the hyperbolic cosine of 3x dx. And we're going to do it by integration by parts. And when we do integration by parts, in this case, what we want to do is we want to differentiate the x in order to turn it into 1. So that will simplify the integrand and integrate the hyperbolic cosine. So we'll set u equal x, and then the derivative of u is 1. And v prime, the term we'll integrate, is the other term, the hyperbolic cosine of 3x. And when we integrate that, well, the integral of hyperbolic cosine, as we've gone over, is the hyperbolic sine. But then we also need to divide by 3 in order to account for the 3x that occurs here. Right? If we do the chain rule here, we get the derivative of the hyperbolic sine is hyperbolic cosine and then times 3. So we need to divide by 3 in order to make up for that. All right, and so if we use this in the integration by parts formula, integral x hyperbolic cosine of 3x, what we're trying to do, is equal to u times v. So that's x hyperbolic sine of 3x divided by 3. That's u times v. And then minus the integral of u prime times v. So u prime is 1 times the hyperbolic sine of 3x divided by 3. And cram that dx in now. All right, so when we apply integration by parts, this is the formula we get. And we still need to do this second integral here. The integral of the hyperbolic sine of 3x divided by 3. And when we do that integral, well, when we integrate the hyperbolic sine, we get hyperbolic cosine. And then we need to divide by another factor of 3 to account for the 3x in the argument of the hyperbolic sine. So that will give us 9 in the denominator, and then plus a constant. All right, and so this is this indefinite integral. All right, are there any questions? Yes? So you asked, why did it become 9? Because like when we integrated the v prime here, we got a 3 because of the 3 here, the 3x. Right? When you differentiate this hyperbolic sine of 3x, you get hyperbolic cosine of 3x times 3. So you have to divide by 3 to make up for that. And we do the same thing here. So because of this 3, we have to divide by another factor of 3. And so in the denominator, we get 3 times 3 is 9. Right? If you want to, you can also do a substitution u equal 3x and then work it out with more detail. Yes? No, so you're thinking of the regular sine and cosine, where the integral of sine is negative cosine, but the integral of hyperbolic sine is hyperbolic cosine, no negative sign. All right, continue. All right, so the other topic from last week that I didn't get to in the previous review session, was Macaulay brackets, which I think is a new thing, probably for everybody. And this is really a system of notation for describing discontinuous functions or functions with discontinuous derivatives. And the notation is given here on the slide. So when we have the Macaulay bracket, it has this sort of angle brackets with the 0 exponent. That's a step function, a function which is 0 up until a, and then jumps up to 1. So we have this x minus a here, and so the fact that it's a here is what it tells us that the jump is at 1, and then It's just 1 if what's inside the bracket is greater than 0, and 0 if what's inside the bracket is less than 0. So this gives us a jump. And then we also have a Macaulay bracket with no exponents. Here we have the 0 here, and then there's no exponent. You can also think of it just being 1 there, but just omit the 1 in this case. And that gives us this ramp function. So it's just equal to x minus a, what's inside the bracket when x minus a is greater than 0, and it's equal to 0 when x minus a is less than 0. And then we also have this Macaulay bracket squared, and the graph of that would be shown here. So this one with the exponent 2 is literally just this first one squared. So it's 0 when x is less than a, and then the sort of half parabola when x is greater than a. All right, so this is the notation. I'm going to do an example of expressing a function which is given in this multi-part way using Macaulay bracket notation. So we have this function which is given on the slide, and I will show how we can express this function using Macaulay brackets. Right, and so the point of the Macaulay brackets is it gives us a sort of more convenient notation for expressing functions like this. Instead of having to divide them up into all the parts like you see on the side screens, you can write them just a sort of way that we're more used to, and then actually you can also do calculus with them, integrals and such in a natural way. So let me first of all draw the graph of this function. You can see it on the sides. And so this is going to be our x and y axes. Right, and so first, I draw the graph from left to right. So when x is less than or equal to -1, it's just 0. So the graph just goes along the x-axis there. And when x between -1 and 1, it jumps up to 1. This is 1. Jumps up here. And then when x is between 1 and 2, the formula is x plus 1. And so it actually jumps up to 2, and then it looks like a line with slope 1. Goes up to a maximum of 3. Drawing these dashed lines in to show clearly what the values are. So in between 1 and 2, it's this line with slope 1. And then in between 2 and 3, it's just constant 2. And then in between 3 and 5, it's this function 5 minus x, and that's just a slope -1, goes down to 0. And then it is constant here, or constant 0 for x greater than 5. All right, so kind of complicated looking function, just some example, but the point I'm going to show is that you can express this type of function using Macaulay brackets. So let's do that. Okay, we have this function of x. So the way that you want to do this, if you are given a function like this or a graph and you want to express it using Macaulay brackets, you go from the left, so from x negative or smaller, and every time you encounter a change in the definition, you need to add some Macaulay brackets in order to account for that change. So let's go from the left and start with this jump here at x equal -1. And so we take this jump at x equal -1. And we just use this Macaulay bracket, which gives us the step from 0 to 1 at x equal -1. So if we only had this Macaulay bracket, the function would just be 0, and it would jump up to 1, and then it would be flat for all x greater than -1. All right, so that gives us this first jump here. Okay, and so now we're going to add some terms that correspond with this jump and the change to slope 1 at x equal 1. So in order to get this jump, we add this Macaulay bracket. So this Macaulay bracket gives us the jump up. And if we only had these two, it would actually just be a flat function from here. So it would be just constant equal 2 for x greater than 1. But it's actually has slope 1. So we need to add another Macaulay bracket here in order to get this line. And so if we only had these three terms, the function would just continue like this Okay, but now we add more terms in order to get the jump down. And so this jumps down 1, so we want to subtract the Macaulay bracket because it jumps in a negative direction. It jumps at x equal 2, so this is x minus 2, 0, Macaulay bracket. That would give us the jump down. And if we just have these, the function would look like that. But we need to make it a flat line, so we also need to subtract this term. So we subtract this term in order to change the slope of this line from 1 to 0. Okay, and then we have another change at x equal 3. And there's no jump here, so we don't need a Macaulay bracket with the exponent 0, the step function. We just need to change the slope to negative 1. So we subtract Macaulay bracket x minus 3. And then finally we have this change at 5. And the slope changes here from negative 1. If I only had these ones that I've written, this would just continue down like this with slope negative 1. We need to add a term to make it so that it becomes this flat line. And the term we need to add is x minus 5, Macaulay bracket. So here we had slope negative 1, and we add this in order to make it a line with slope 0, a flat line. Sorry, can you? Okay, the question, why is there not a step function at 3? Why this one? Because so if we didn't have this one, then the function would just continue like this. So we have to add this one, or subtract this one, in order to change it from slope 0 to slope negative 1 at 3. Right? This is 3 where that happens. Okay, so it's an example of using Macaulay brackets to express a function like this, yes? Okay, so the question is, what's the difference between these two terms, x minus 2 power 0 and x minus 2? So this is from the definition of the Macaulay brackets you see on the sides. So the 0, when there's a 0 exponent, that's a jump. And when there's nothing there, then it's the ramp. Okay? All right. I know this is new material, and I think it can be take a little while to get your head around, but there's also examples in the videos and example sheets. All right, let's continue. So that was material from last week, and now you can move on to the material that is covered in the videos this week. And the first thing was about double integrals. And so in order to discuss double integrals, I first put this slide up to remind you about single integrals, single definite integrals. So I actually also discussed this slide last time. When we just have this single integral, it's important to understand that it represents this yellow area, the area between the graph and the x-axis between the two limits of integration. So when we have a double integral, instead of taking an area, the integral represents a volume. And it's a volume in between the graph of a function of two variables, f of x and y, and a region in the xy plane that's called R here. So this capital R underneath the double integral represents the region you integrate over. So you see in one dimension, all regions are really just intervals, and so we just have two limits. But in 2 dimensions, you could take a general region in the xy plane and integrate over that. We only discuss rectangles and circles and sort of sectors of circles in this class. But in general, you could do a double integral over an arbitrary region R, and that represents the volume between the xy plane and the graph of the function over that region R. So this is an analogy with the one-dimensional case. So let's look at an example, a simple example of a double integral. So suppose R is this rectangle for x is between negative 1 and 1, and y is between negative 1 and 1. Actually, it's a square. What is the double integral of over that rectangle of this constant function phi? 5. So there's a pole, which you should see. and select what you want to put. Okay, well, let's continue. I'll show you the results. So the most common answer was 20, which is the correct answer. And so good job if you put that. Let me explain why it is. And so in order to do this, you can realize that this double integral represents this volume. And so we have this double integral over r of the constant 5, where r is the set where x goes from -1 to 1, and the same for y. Okay, and so let's draw this, a picture of what volume is represented here. So I'm going to draw these x, y, and z axes. So this is representing a three-dimensional space in 2 dimensions. So we have the x, y, and z axis. The region R is where x goes from 1 to -1, and y also goes from 1 to -1. And so the region R is this square. And so this is a square in the xy plane. And then the function that we're integrating, the integrand is constant 5. And so the double integral represents the volume above the region R and below the graph of this function, which is just constant 5. And so this is actually the volume of a cuboid with height 5. And so we can calculate the volume of this cuboid with height 5. The height here, I haven't really drawn it to scale, of course, because at the base it's 2 by 2 and the height is 5. But the height is 5, and the sides, so it goes from 1 to -1, so the sides are length 2. And so the volume of this cuboid equals that area of the region R at the base, 2 times 2 times the height, 5, and so that's 20. So the volume of that cuboid is 20. That gives us the double integral. Okay, so for this one, this is pointing out that these double integrals give you this volume. All right, we could also calculate double integrals by converting them to iterated integrals. Sorry. And so when we have a double integral over a rectangle R, we can convert it into an iterated integral, which is where we do the integration with respect to one of the variables first, and then the other variable second. And we refer to this as the iterated integral. And so if we have this rectangle where x goes from a to b and y goes from c to d, we can write the double integral integrating with respect to either one of the two variables first. So in the top there, we integrate with respect to x first, and we just hold y constant and do this integral with respect to x from a to b between the limits. And then once we've done that, we do the outside integral and integrate the result with respect to y. And you can also do it in the other order. So somewhat like how for partial derivatives, you can differentiate either with respect to x first or y first when you have a mixed second order partial derivative. You can do these iterated integrals in either order. Right? In some cases, it turns out to be easier to do one or the other first. All right. So you can do it either way. And so let's look at an example of this, where we do a double integral where the integrand is not just constant. We have to do a iterated integral. So I'll give you a poll and see which variable you think we should integrate first, x or y. So which one should be the inner integral? So no calculation required on this one. Just tell me what you think. All right, let's show the results here. So most people think x. In fact, in this example, it doesn't work to do x first. It's sort of a trick question. It works only to do y first. So let's have a look at that. So I wrote down the double integral that we're trying to do here. And in order to see why it won't work to do x first, let's try to do x first and see what happens. So we'll write the iterated integral here. So the x integral goes from 0 to 1. The y integral goes from 1 to 2. Right, so how should I try to find the indefinite integral for the x one? Well, you could try to do it. You could do it by integration by parts, setting u equal xy and v prime equal e to the x y squared. And then the derivative with respect to x is just y. And you integrate this one with respect to x, you get 1 over, you get, let's see, v would be 1 over y squared e to the xy squared. All right? And so if we try to do integration by parts in order to calculate this indefinite integral, you get u times v, so that's x over y e to the xy squared. That's u times v minus integral of v prime times u. Oh, sorry, u prime times v. So that would be 1 over y e to the x y squared. And then we'd have to do this one. We would get minus e to the x y squared over y cubed, it looks like, plus c. All right, and then you would have to do the integral of this with respect to y after you've plugged in some values of x. And we can't find integral of e to the y squared over y cubed. It's just there's no way to do that. So that's why we can't do the x integral first. Let's try to do it the other way. So maybe you can try to do some more if you want, if you don't believe me, but it won't work. So let's do the other way. Try y integral first. So we start again from the beginning. Double integral xy times e to the xy squared dA. And let's set it up the other way around. So the x will be the outer integral, the y will be the inner integral. Okay, and so, well, you can do this one by substitution, the integration with respect to y by substitution. You substitute in u equal xy squared. I'm going to skip some steps here just in order to save time, but if you do that integration, you can get the indefinite integral is e to the xy squared over 2. Okay. Once again, just substituting u equal xy squared. And you can also just take the derivative of this with respect to y. You get xy e to the xy squared. Okay, and so this is already looking a little bit easier, as you can see. And so we have the integral from 0 to 1. We need to evaluate this indefinite integral between the two limits. And so when we evaluate at y equal 2, we get e to the 4x over 2. When we evaluate at y equal 1, we get e to the x over 2. And so let's plug it in y equal 2 and y equal 1. And now you can do the indefinite integral of those exponentials fairly easily. Oops, sorry. So let's do the indefinite integral first. So the indefinite integral of e to the 4x over 2 is e to the 4x over 8. And we need to divide by the 4 in order to account for the 4x. And the indefinite integral of e to the x over 2 is e to the x over 2. We need to evaluate that between x equal 1 and x equal 0. And so in order to finish up, we just have to plug in the limits. All right, so, oops, sorry. So plug in x equal 1, you get e to the 4th over 8 minus e over 2, and plug in x equals 0, you get minus 1/8 plus 1/2. Okay, and maybe you can combine those together, but let's stop there. So this is the value of this double integral. This is an example where it's much easier to do the y integral first. In fact, I don't think it's possible to do the x integral first. Any questions? Okay. Let's continue. All right, so we also covered how to do double integrals using polar coordinates. And so when we use regular x and y coordinates to do the double integrals, that's natural to do integrals over rectangles, like, as in the example that we just looked at. But if we want to do integrals over different shaped regions, we might want to think about doing using different coordinates that are naturally suited to those regions. And so polar coordinates work well for disks, that's the region inside circles, or sectors of disks. And we can use polar coordinates in order to do double integrals. So polar coordinates are what we get when we specify a point in 2 dimensions by its distance to the origin. That's called r, and the angle it makes with the positive x-axis, which we call theta. So it's illustrated in the picture at the top. The regular Cartesian coordinates, x and y, are related to polar coordinates using trigonometry. X equals r cosine theta, y equals r sine theta. And when we want to do double integrals using polar coordinates, the key point is that the area form, dA, that we have in the double integral, needs to turn into r dr d theta. So when we use x and y coordinates, dA is just dx dy. When we use polar coordinates, we need to replace dA by r dr d theta. And there's a sort of heuristic explanation of why this is true in the videos. It's essentially that if you consider a small little rectangle with a unit, or the small, given by a small change in the angle and a small change in r, the area of that rectangle depends on r. And so that's why we have to do this. All right? And so, well, let's look at an example. Suppose we want to do this double integral where r is a disk centered at the origin, so it's centered at the point x equals 0, y equals 0, disk of radius 3 of this function, e to the negative x squared minus y squared. So we want to do this in polar coordinates because it's an integration over a disk. The first thing that we need to do is say, what is this function expressed in polar coordinates? And so I'll let you answer that. Give a minute. All right, I think that's long enough. I'll show you the results. And so option 3 is the most popular one. Sorry, that may not have too much meaning, but that is the correct answer, e to the negative r squared. So good job if you chose option 3. This function expressed in polar coordinates is e to the negative r squared. And if you're unsure about that, let's explain it. So we have double integral over this region r, e to the negative x squared minus y squared dA. And r is the disk of radius 3 centered at the origin. So we draw the xy plane here. And this is 3. And r is the disk centered at the origin of radius 3. And, well, maybe the most straightforward way to see what this is to remember that polar coordinates are related to the xy Cartesian coordinates by the formula x equal r cosine theta and y equal r sine theta. And so if we plug that into negative x squared minus y squared, you get negative r squared cosine squared theta, that's x squared, minus r squared sine squared theta, that's y squared. And so then you can factor r squared out, negative r squared out. So this is negative r squared times cosine squared plus sine squared, which is equal to 1 by the Pythagorean identity. So negative r squared. And so e to the negative x squared minus y squared is e to the negative r squared. Okay? And so let's do this integral in polar coordinates. So first, we use the fact that the integrand is e to the negative r squared. And then dA, remember this is the key point, dA is r d theta. And so we r dr d theta. And now we can write this as an iterated integral where we integrate with respect to either theta or r first. So e to the negative r squared r. Let's do the integral with respect to r first. And so this is a circle of radius 3. So the radius r goes from 0 to 3 in this disk. And this is the entire disk, and so the angle goes all the way around the disk from 0 to 2 pi. Okay. And so this is the double integral once we set it up as an iterated integral. Okay. And so let's do the indefinite integral with respect to r. So e to the negative r squared times r. The indefinite integral is negative e to the negative r squared over 2. All right, and you can do that by doing a substitution u equal negative r squared, or you can just check that I've got it right by taking the derivative of this, using the chain rule, and seeing that you get the integrand. And so this equals integral from 0 to 2 pi. We plug in 3, we get negative e to the negative 9th divided by 2. If we plug in 0, we get plus 1/2 theta. All right, and now this is, theta doesn't appear here, so this is just the integral of a constant from 0 to 2 pi, and so that's just going to be 2 pi times the integrand. So 2 pi times negative e to the negative 9th divided by 2 plus 1/2. And if we want, we can simplify this by factoring out the half, which cancels with the 2 and the 2 pi. And so this becomes pi times 1 minus e to the negative 9th. Pretty close to pi. All right. There, that's that example. There's not any questions on Slido, so I don't think I'm going to go on to another example. There's not enough time. But if you do want to ask a question, you can raise your hand or put something into the Slido. I'll answer now. Yes? Sorry, I can't hear. Sorry, can you talk a little bit louder? Yeah. Oh, the notation. So I think you're asking about why I put one bracket curved and one straight. So that's just the notation that I like to use in order to indicate that I'm evaluating that function between the two limits. So here, I'll show you. So the question is about this notation here. It's a notation that I use, and I guess the general definition is this. We have a function, and we have A and B here. And it's just defined to be f at B minus F at A. It's just the notation that I use for that. Okay, well, if you want to ask any more questions, you can come up here. Oh, someone asked about the deadline for the diagnostic follow-up. It is next Friday, the 22nd, at midnight.
So here it's A is negative 1. So x minus negative 1, x plus 1. So this is x minus negative 1. Right? We've taken A, negative 1. X minus negative 1 is x plus 1. And then...
My question is, why did you take minus 1?
Well, I can understand. So here, in this one, x minus negative 1. And that is x plus 1. Here, it's x minus, so that gives a jump up from 0 to 1. And then this one, it gives a jump at x equal 1 up to 2.
These are the only jumps.
Yeah, well, there's also
What does this indicate? Like you do this from here, or you do this from jump?
I mean, I think it's sometimes clear to graph it and see what it is. Yeah, I mean, it's just an example. I think that questions could be set up in a different way. So it's an example of how it works.
This one would help us disregard that. Now my question is, how can you get that? How can you get 18?
So from negative 1 to 1.
Minus 1, right? From here, x minus 1, equal in bracket 0.
Yeah.
Same thing, let's do the second one. Second one, let's put it in 0.
I don't understand what you wrote here. So it looks like you wrote the brackets and then you have negative 1 less than x less than 1.
Yeah, I just put bracket. I put this.
Yeah.
I put this here. Our 0 is equal to 4.
All right, so I mean, these are different things, right? These are inequalities. And this is a function of x.
You got this just with x minus 1. How did you get this? I don't know.
It's because it jumps up at, I mean, so, right, maybe I should have been a bit more explicit here. The, like, definition of this notation is equal 1 if x is greater than 0. At 0, x is less than 0. Right? It's this jump.
This one is just talking about jump. That's it.
Yeah, and so here we have x plus 1. So this equals 1 if x plus 1 is greater than 0. I just plug that in. And 0 if x plus 1 is less than 0. And, I mean, you can change those to the x greater than negative 1, x less than negative 1. So it jumps